Hello and welcome to Chapter 7, Cryptographic Systems. In this chapter, we are going to cover all the different types of cryptographic services. We'll talk about authentication, integrity, and confidentiality, and the different types of protocol that allows you to have confidentiality, integrity, and availability. We'll talk about the PKI, the public key systems, and how devices request and retain digital certificates, digital signatures. You'll know the difference between symmetric and asymmetric cryptography, everything that you need to know about cryptography and how it works. All right, so let's get started. When it comes to cryptographic services, it really comes down to you want to take care of authentication. How do you make sure that the user that logs into your network that's authentic? You validate that user. So the data that's being passed over the internet, let's say, you want to make sure that it's really the person that is supposed to be logging in is the one that logs into your network. So you want to validate that. Integrity, you want to make sure that the data that's being passed, this guy right here does not tamper with it or make changes to it. So you want to make sure that the data that's being sent by the user is the data that is received at the other end. Confidentiality means that you want to make sure that this guy doesn't see the data. Not only never mind tampering with it, but it does not see the only authorized users are supposed to see the data, the sender and the receiver. How do you protect the confidentiality of the data? We're going to, of course, use integrity. How do you protect the integrity of the data? We use a hashing program, and authentication also will use a hashing program. As well, you can also encrypt the data. And what's the difference between hashing and encryption? We'll talk about those in a minute. Authentication. Again, authentication is validating the user, making sure that the user is the person that is supposed to be accessing the network or accessing the device. Data integrity, again, is to make sure that the data that's being transmitted is the same data that's been received on the other end. All right. And confidentiality is to make sure that only authorized users are the ones that are supposed to view the data, the sender and the receiver in this case. All right, so let's talk about cryptography and how we can do this. Protect the authentication, integrity, and the confidentiality of the data while they are in transit, while you are transmitting them. If the data is locally, then you can use BitLocker or the different types of protocol that you can encrypt the data locally so no one can view them. All right, how do you encrypt data? When it comes to encrypting data, there are three different methods. Mostly the first two is being used: transposition, substitution, and one pad. Transpositioning, meaning really you shift the data. For example, if A, B, C, D is what you're trying to do, you shift the data by 3 letters. Instead of sending A, you'll send D. Instead of B, you'll send E, and so on. On the other end, all you got to do when you receive this, you shift it back 3, and you'll be able to read the data. All right. So that's really transpositioning. Julius Caesars in the old days, in the old Roman eras, they were able to do something similar to this by transpositioning the letters, and they were able to encode messages while they were at the battlefields. So transposition, for example, let's say flank east, attack at west. What you could do is not only that, you can place the sentence that you want to transmit on 3 different lines. So for example, what you do is you put the F and you skip 3 letters, you go to the next line, you skip 1 letter, you go to the 3rd line, you skip 2 letters to write it out. And then you write it out. With transpositioning, you are not really substituting any letters like the other one. So what you're doing is then you start reading. you read the first line, the second line, the third line, and that's what comes out. So what you do when you get this is you know what the key is. You put the first letter, and then the second letter comes from the bottom here, the third letter, and so on. All right, so you just know what the key is. You know that he waited 3 letters before he put the K in, and then waited 3 letters, put the T in. So what these 3 letters in here, you put the L, the A, and the N. So you go to the second line and you pick 1, missing 1. Second line, 1, missing 1. So that's how these guys go up here, right? So that's really one way of doing it. You can switch this many different ways. And by the way, once you either use substitution or transpositioning, once these come out, then they go there and then they are converted into ones and zeros because each letter is assigned an 8-bit number according to the ASCII code, the American Standard Record Information, and then you get a key, and then you XOR. If you know what logical XOR is, I'll show you that in class. And when you take each letter and you XOR it, what comes out is the encrypted ones and zeros, the binary data, and that's what you transmit. So there are really 2 steps. You either move if it's data, if it's alphabetical data that you're trying to send, you convert that into ones and zeros. Everything has to be converted into ones and zeros, video, voice, or data. Once that's converted into ones and zeros, and if it's one, and what you do is you end it with, you XOR it. That's the encryption. You XOR that with a key that you are given. That key could be the same key or a different key. We'll talk about a different key than the one that the receiver has. We'll talk about that when we get to it later on. And that's what really encryption is. The different techniques on how to really substitute or transport or transposition the letters, and the keys could be when it comes to the binary keys, they could be extremely long too. All right, so here's the substitution. Like I said earlier, you're just substituting the letters. The other one was transpositioning. This is a little, but both of these are very easy to break. So there's many different techniques of doing all of these. All right, the one-time pad is creating a random phrase or letters or numbers that these will create, and you can use those to encrypt the data. It's very difficult to do because today's computers use mathematical equations to create numbers, and that is not really random. Because if somebody can figure out what how your computer creates these quote-unquote randoms, they can always pick out a key. So it's not always as random as you think, because computers do have to come up. They have to use some sort of a technique to come up with these ones and zeros. All right, so these in the old days, no one really bothered with this one-time pad. All right, so let's talk about cryptanalysis. Cryptanalysis is the way you crack the code. You analyze the actual code and trying to figure out what the code is. That's been done in World War I, World War II, all the way back to, like I said to you earlier, in Julius Caesar's time. If you can figure out what the code is, then you can figure out what the data that's being transmitted, and that could mean in a battle that you can win the battle very easily, of course, when it's between organizations, and you figure out what that sensitive data that's being transmitted. It could be the end of companies. All right, it could be a financial disaster, for example, for an organization. So you want to be sure that you use the most sophisticated encryption keys, and it makes it very difficult to crack what these keys are. So there are several methods on how to crack a code. So here are, and I want you to write these down. There is the brute force method, the ciphertext method, known plain text method, chosen plain text, or man in the middle. meet in the middle. We used to call it MAD in the middle method. Crypto analysis is what the NSA really looks for. They're looking for individuals that can crack codes. I mean, constantly. This is a big job. There's always a job opening at the NSAs for crypto analysis. All right, so here's a method, for example, for cracking code. We know in all the English language, for example, that the letter E, 12% of the time, 12% of the words, a little bit more than 12% of the words, have the letter E in them. For example, Z or X, there's hardly any letters that have the letters Z and X. So whatever you are transmitting, you can figure out, for example, depending on the frequency. So you can, for example, you say, wait a second, here's the letter D. It happens so many times. If it's 12%, then you take a guess and you say, oh, most likely it's probably E, because it happens so often. And you can play around with it this way, depending on the frequency. And then you can take a guess and, something may come out, right? Cryptography that's when you actually means cryptology is the cryptography and crypto analysis. It's really how do you encrypt the data and how do you crack the code, right? That's what it comes really down to. That's why cryptology, the science of someone who is able to encrypt and decrypt the data, or figure out what the code is at least. All right, so like I told you earlier, crypto analysis, NSA always looks for, there's always job openings at the NSA. If you go there now, you'll probably see one. Excuse me. All right, so let's get into the different types of cryptographies. When it comes to authentic integrity, making sure that the data that's being sent has not been tampered with, there are really mainly two different types of protocol, two different engines that will hash data, hash your message that you're trying to transmit. The message digest number 5 and the secure hashing algorithm. SHA is a little bit more sophisticated than MD5, but MD5 been around for a while, so both of them are used to both of these hashing program really is a technique to make sure that the data that you are transmitting or even sitting locally are protected. When it comes to authentication, you want to use the HMAC MD5 or HMAC SHA. Both of these methods really protect and make sure that the passwords that you are transmitting are secured, and there's non-repudiations, meaning that the sender cannot say this is not me, it has to be you, by using the HMAC MD5 or SHA-1 or there's SHA-2 and there's SHA-256 as well. When it comes to encrypting, making sure that the data is encrypted. By the way, in these two methods, the data is actually not encrypted, but it cannot be tampered with. For this one, you'll know if somebody changed the data on the way. That's what hashing really does. It does not necessarily encrypt the data, although you can just transmit the hash. And if you transmit the hash, you can call that encryption, because the key, the actual hash that you are transmitting is not the actual data, though. But we'll talk about that in a second. Excuse me for a second. With authentication, also the data is not encrypted. Here, the actual data, when it comes to confidentiality, there's 3 different protocols: the DES, the triple DES, and the AES. The data encryption standard, or the 3 triple data encryption standard, and the advanced encryption standard, all 3 methods using symmetric key to encrypt the data using the XOR, like we talked about. Instead of using the logical ANDing, you use the XORing. We use ANDing to figure out what the subnet of an IP address is. Here, when you XOR, you create an encrypted piece of data before you are transmitting it. This is where the actual data gets encrypted. All right, so please write this table down. So this way you'll know the different types of protocols that you want to use if you want integrity, authentication, or confidentiality. Okay, so let's talk about integrity and authenticity and the different types of protocol that are out there. Okay, what is a hash program? So let's talk about hashing. That's the MD5 and the secured hashing algorithm, the SHA. The MD5, well, the hashing does this. It takes a piece of data, whatever you want to transmit, either a password or a big message, and once it goes through the program, the hashing program, the MD5 or the SHA, it comes up with a number, a fixed length hash value. Fixed length meaning, let's say that this is a 16-bit number. No matter how big the data is or how small the data is, when it goes through the hash, you'll get a 16-bit number. Now, this number is unique to the data. It's almost, 1 in a billion chance that the two different pieces of data will have the same hash. So if you change one letter in the message, and when you go through the hash, a different number will come out. But if you put the same exact data in, the same number should come out. So every piece of ciphertext, we call it, or a hash, every hash is unique to the same data that goes in. The good thing about hashing is if you send this out or you save this on your hard drive, or somebody got this, they will never be able to go back and figure out what the actual data is. So it's just a number that's unique to this, but if somebody just looks at this, they can't figure out what the actual piece of data is. So for example, this is what they do on your what do you call it, the ATM cards. So when you type in your number, let's say 123 is your key for to access your excuse me, to access your ATM card. So you type in the number, a hash will run, and that hash is what's saved on the ATM card. So when you put in your ATM card and you type in that number at the machine actually runs the same hash. It comes up with a number and then compares it with whatever you have on your card. And if it's the same, that means you're in. You get your money. If it's not the same, of course, it's going to reject it. So if you lose your card and somebody was able to get this number, they can't figure out what your actual key is, right? If you save this on, let's say it's for a password, and this is saved on your computer, and you lose your computer, somebody figures what this out, and they won't be able to figure out what your data is. But the problem is, you figure out what your password is. The problem is, let's say you use the word Cisco, and this number came out as the hash, your password is Cisco, and it's saved on your drive. So you go home, even though you can't figure out that this is Cisco. So what you do is you run, for all the dictionary words, you run the hash program on it, and every number that comes out, you start comparing it with this. Eventually, you're going to get a hit. So therefore, that's why it's highly recommended when you are typing passwords that you use them be long and not a dictionary word, right? Make something up that it's almost impossible for somebody to figure out what your password is, because you don't want these brute force programs to try to guess. Okay, so that's what really hashing is. By the way, so what do I do? I know we're spending a little bit more time. I want to make sure you understand what hashing is. So let's say I want to send a message. So I want to tell you that you guys, we do not have class the following week, for example. Or let's say I wrote everybody is getting an A. I don't know about that, but let's say everybody is getting an A, and I send an email to everyone that everyone in the class will be getting an A. But how do you know that this really came from me and not somebody else? So what I do is I put this into the hash program, and this comes up. I put the message, everyone in class is getting an A, and I run it through the hash. I take this number and I stamp it on here, on the actual data, and I send the message, the same message, everyone is getting an A, with the hash attached to it. So when you receive it on the other end, the first thing is you're going to do is you're going to run the same message that I transmitted to you in the hash. The number that comes out, you compare it with the one that's stamped on it. If it's the same, you know it's authentic, right? You know it came from the professor. No one really played around with it. The only problem is when I'm sending the data, for example, and somebody looks at the message, at the hash, they can play with the hash, change the numbers. So the message will always be, oh, he's not the professor. We'll just ignore it. So what we do is we're going to encrypt this with a key before you place it on here, before you send it out, right? So you got the message with an encrypted hash. So nobody can change the numbers, right? Let me just go back, right? That's what digital signature is, because as we will talk about later on, the encrypted hash is really what digital signature is, okay? But we'll talk about that later on. So hashing is to prove that the data that's being transmitted has not been tampered with, right? Okay, so this really explained what I just went through, right? So if it's not the same, then you know that the data that's transmitted, has been tampered with, changed from $100 in this case to $1,000. All right, so the different types of hashing that are the same thing with the message digest number 5. You get 120-bit hash message for whatever the data is. Message digest number 5 has been created for many years. It's been used when we use the enable password, enable secret password. That password is encrypted in an MD5 hash. That when you do the show run and you see that number 5, you know that means that the password is encrypted in message MD5. It's 128 cipher text or hash that you get out, and that is unique. Will always be 128 bit. If it's a password like the word Cisco or a whole document, the same fixed length of 128 bit will come out. The secure hash algorithm, the SHA, different types of lengths, but they are unique. SHA 1, 2, or 100 or 256. This is a little bit more stronger than MD5. SHA is mainly used with VPNs, which we'll talk about next week, and MD5 mostly for passwords. A little bit faster with SHA, but both of them are pretty secured. Here's a comparison between MD5 and SHA, and you can see that the ciphertext is much longer with the 256-bit SHA. This is much stronger, but it takes a little bit longer to create and decipher. All right, the HMAC, and we talked about that too. Instead of just sending the plain message, you also have a secret key attached to it. This is what really creates a digital signature. So what you do is you'll have a key, and you take the message, you run it through the hash, and you'll have and when you run it through the hash, you'll get a fixed length authenticated hash. Then you take a key and you encrypt it with, we'll talk about keys later on. You encrypt it and you place that right on the actual data. That's right here, right? You take the same plain data and you put the hash with it and you send it out, right? This is for authentication purposes, to make sure that it came from the professor. So when you receive the message, the plain text message with the encrypted hash, it's been encrypted with a key, you receive it, right? The first thing you are going to do is you have the same key on the other side. So you take the encrypted hash that's been stamped on there, like my signature, right? And you decrypt the encrypted hash. If you get the hash number, then you okay. Then what you do is, once you get the hash, then you take the plain text message, you run it through the hash function, and what comes out, you compare it with the hash, the decrypted hash that you already decrypted with the key, and you'll be okay. Understand? Now, for that means you know that it's authentic. And by the way, and we'll talk about why, because anybody can get the key. That's correct. And the only reason you're going to be able to decrypt it, if you decrypted the data, okay, and you were able to see the hash after you decrypted it on the other end, you have no doubt that I am the one, the professor is the one that sends the message. Why is that? Because if you were not able to decrypt it, that means there's no way I would have the professor send it, because the way it works is I'm the one who gave you the keys, right? I give everybody a key. Called the public key. I know we're going to talk about that later on. And I keep another key called the private key. The private key is the one that was used to encrypt the data. And the only other key that can decrypt it is the one that I gave you, to give everybody. Okay, even the one that I use, the private key that I encrypted the data, it cannot decrypt it. The only one is the other key, his friend. So since everyone only has public keys, they won't be they can decrypt the data, but they won't be able to encrypt it. If somebody used a different key to encrypt this message, other than the private key that I have, you will not be able to decrypt the data. It's impossible. The only key that's going to be able to decrypt the data is if it was encrypted by the private one that I have. And if there's only one key and it's private, means because I kept it with me and I didn't give it to anyone. That's called asymmetric encryption. So when you were able to decrypt the message digest, you know for a fact that I am the one who sent it. That's non-repudiation. I can't even say that I did not encrypt it, because it's almost impossible. Those keys are very, very huge, and they're created randomly. It's impossible that two different keys are going to be the same. So because it has to be me, right? That's what authenticity means. And that's what digital signature is. Digital signature is the encrypted message digest, the encrypted hash that is playing on a message and being transmitted. Okay, this is called the key hashed message authentication code. We are going to make sure that the password that's being transmitted is the password that are the actual password that's or the actual user that who is sending out the data. Okay, so that's for authentication. That's the HMAC, the message authentication code. All right, so that's what I try to explain to you. If not, we'll talk about that more in class. We'll go over it a little bit more. Excuse me. All right, so we use the hashing for data integrity to make sure that the data has not been altered, and data authenticity, right? Make sure that the data is authentic and it came from the right owner, not somebody else gave it to us. That's the HMAC. All right, so when we talk about keys, which is really a fixed number to do the XORing, somebody needs to generate them, verify them. How do we exchange the keys? How do we store them so no one has access to them? And if someone has access to them, they won't be able to figure out what that data is. And the key lifetime, because as we will discuss later on, the keys that are given between two users are always going to be the same, symmetric key rather than asymmetric, they're only going to have a little bit of lifetime. It may be, we'll set a lifetime to how long the keys can be used, and we have to renew them. Because if you just use the same key forever, somebody will eventually guess it. And then we're going to talk about where do we store the key revocation, and how do, if you get rid of a key, the key revocations and destructions of the keys. We're going to make sure we keep track of all the keys that are not being used or have been compromised in a list. All right, so there is a certificate authority that keeps track of, you know, all of this. How do they? All of this is done by a different third parties. Okay. So, for example, if a company wants to have people from outside accessing their network, what they do is they'll have a ways of generating keys, verifying it, exchanging it, giving you a key. Like VeriSign does that to allow you to do HTTPS very quickly. They give you digital certificates and all of those wonderful things, but they got to maintain the key. And how do they, where do they go after they've been compromised, to make sure that we always check the revocation table to make sure that the keys that we are generating, they have not been used or been compromised. That's where it comes down to. That's the PKI, by the way, the public key infrastructure, how to manage all of these different keys. All right, key length and key space. When it comes to key, the longer the key, the more time it's going to take to figure out how long that's the data is going to, the time it's going to take to crack the key. So look at this, for example. The advanced encryption standard takes 149 trillion years to crack. That's a very, very long time. So it's pretty safe. And with the AES, you could take the key and just if you encrypt with AES, which is the most widely used encryption method for VPNs, it's pretty safe, I would say. And those keys are really created one time and randomly. Like I said earlier, randomly may not be the right word, but random, 149 trillion years is pretty good, right? All right, so key space is how the number of possible keys, different keys. So if you have a 256-bit key, there are 72 with that many zeros ways to figure it out. So that's how many times you have to go through to really guess what the key is. Different combinations of ones and zeros. That's what that means. If you have a 60-bit key, look how long it grows to, just an additional 4 bits. So it's exponentially, it becomes harder and harder to figure out. The key space increases the amount of time that it's going to take to guess what the key is, right? So the longer the key, the longer the key space is, the longer it's going to take to figure out what the password is to crack it. All right, there are 2 different types of keys. There are symmetric and asymmetric keys. And here are the different types, protection for 3 years, for 30 years. So you can have protection computer against quantum computers. So it tells you for symmetric keys, you can have 80 bits, 96, 112 if you want, 128-bit symmetric keys is probably the one that you use if you want protections for 128. If you need 128 bits. So they're all pretty good. Regardless, I would say, as long as you encrypt the data, then you have not much to worry about. Let's take a look at symmetric key. Well, let's continue with the shorter the keys, the faster the processing. Of course, you can encrypt the data much quicker, but less secured. That makes sense. The longer the key, it's going to take, the process is going to be a little bit slow, but it's a lot more secured, of course, and because it's much harder to crack. So you probably want to use, I think, 512 keys or even 128 is the safest. You can create keys even 1024, 2048 when it comes to RSAs, if you remember. All right, so let's talk about now symmetric keys. Let's talk about encryption. There are two different types of symmetric keys, and I want you to write this down so you'll know the different types. When it comes to symmetric keys, that means you, the sender and the receiver, have to have the same keys. So before I send you the data, I will take the key, I will encrypt it with the data and send you the encrypted message. On the other end, you take the same key that I had and you decrypt the data. So data is encrypted and decrypted using the same key. That's called symmetric, means, or pre-shared sometimes we call it. That means the sender and the receiver have the same key, right? The problem with this is with symmetric keys is that if somebody gets their hand on the key, then of course they can decrypt all the data that's being transmitted. But the good thing about it, the benefits of symmetric key is it's much faster than asymmetric keying, asymmetric encryption. In fact, it's 1,000 times faster if it's in software. It's 100 times faster if the software is already in the hardware. So you definitely want to use symmetric keys. That's one of the reasons it's 1,000 times faster in hardware and 100 times faster if it's already embedded in the hardware. Either way, symmetric keying, symmetric encryption is much quicker to encrypt and decrypt. And we only do, by the way, over the internet is symmetric. Everybody has the same key. The only thing is we use asymmetric to make sure we pass symmetric keys to each other. And then once we have those keys, we can use them for a certain amount of times, especially when we set up a VPN. And after a certain amount of time, you release these keys and use different keys. And then you regenerate new keys. Okay, so you don't use the same keys forever. All right, so that's symmetric, having the same key, the sender and the receiver, to encrypt and decrypt the data. Asymmetric works the following way. What I'm going to do, I'm the sender. What I'm going to do is I'm going to generate two keys, okay? And they are related to each other. And how are they related? If you encrypt the data with one key, the other key cannot. The other key must be used to decrypt the data. Is that clear? It doesn't matter which key you use to encrypt or to encrypt the data, but if you used one of them to encrypt, the other one is the only thing that can decrypt it. The same key cannot encrypt and decrypt the data. One is used for encryption, the other one is used to decrypt the data. Is that clear? So I'll generate two of them. The one that I keep with me, I'll call that private key, and the other one is the public key. I give it to everybody that wants to talk to me. I'll give the other key that I generated. So what I do is every time I want anybody in the public to send me data, I want them to encrypt the data with that public key that I gave them, right? So when they send the data and I receive it, I'm the only one, since I have the other key, I'm the only one that's going to be able to decrypt it, right? If anyone else, while the data is in transit, captures the data and try to decrypt it with the same key, the public key that I gave out, they won't be able to do it because you cannot decrypt the data with the same key. The only one, again, that's going to be able to decrypt it is me because I have the private key, right? And it goes the other way. If I want to send you for authenticity purposes or non-repudiation, is if I encrypt the data with my private key and I send it out to you, and you guys were able to decrypt it, you know it came from me, because otherwise you won't be able to decrypt it. The only reason you were able to decrypt it because I am the one who encrypted it with my private key. Remember, okay, that's asymmetric, much more secured. impossible to crack because unless somebody has access to the private keys. But the problem is it's extremely slow, super slow. The RSA, when we do the SSH, uses asymmetric key. Diffie-Hellman uses asymmetric keying, but Diffie-Hellman, as we will see later on, and I'll show you in class how it works, is it's used to pass a symmetric key to another guy over the internet securely. And once it's passed, then his job is over, and we'll use that symmetric key to communicate with each other because it's much faster to encrypt and decrypt data using a symmetric key. All right, so please write this down. And if you can really explain the difference between symmetric and asymmetric would be very, very helpful in your own words to see if you understand it. All right, so that's the difference between symmetric and asymmetric. When it comes to symmetric keying, the data encryption standard, that's a symmetric. All these are symmetrics. Uses 56 triple DES using 112 and 168 bit length keys. So remember, the longer the key, the more sophisticated. AES, you can have 256. With AES, there's one way of where you can take the piece of data, and for each block of data, you can encrypt encrypt it 13 times with 13 different keys. And then on the other end, you can decrypt it 13 times. The software encryption algorithm uses 160, and the revert cipher keys, you have RC2, RC4, RC5, where the MD5 is. RC4 is where WEP is. And then you have RC6, which was in competition with AES for the AES, for the encryption method, for the advanced encryption method to use for VPNs. So the reversed ciphers are used extensively in encryptions. Okay, I did mention the RC4 that is the WEP, but it has its weaknesses. We'll talk about that more in class, and I'll show you. I'll have more time on the board to show you how encryptions work and how Diffie-Hellman works and all those good stuff. All right, so you can block or stream cipher block of data. So if you take a block of data and you encrypt it, and you send the encrypted data, and then you decrypt it you take it and you decrypt it on the other end. All right, so you use the XORing. You take the ones and zeros and you XOR. That's what comes out is the encrypted data. And when you transmit it, and you're on the other end, because you're using the same key, you decrypt it with the same key. Actually, you XOR again, the logical XOR. Okay, so which one do you want to choose? I'm pretty safe in thinking if you can always set up your VPNs, for example, using AES, that would be the best encryption. Although triple DES is the most widely used, it has not been cracked since the nobody knows if it's not even vulnerable to being cracked. So triple S is the most widely used, and it's the most respected, and it's still being used for VPNs as of today, but to encrypt and decrypt the data. But AES is really taking traction. It's been around, for close to 20 years now, and when it comes to encryptions, really it's pretty safe to say that it doesn't really matter which one you use. Although DES will be a little bit quicker to encrypt and decrypt the data, but even AES doesn't take that long. It takes less time than triple DES to encrypt and decrypt the data. So that's why more and more software will most likely in the future will stick with the AES, the Advanced Encryption Standard for encryption. Okay, so here is the DES. It's been around since 1976, and I think IBM is the company that came up with DES. Triple des, that means you're going to have 3 different keys. What you do is you take the piece of data, encrypt it, and then decrypt it with another key, then encrypt it again. So it's encrypt, decrypt, and then encrypt with 3 different keys. And then you send the encrypted data. When you receive it on the other end, you decrypt, encrypt, decrypt. You go the opposite way. 4.6 billion years for triple des is not bad. The time to, the key space, right? The time to crack the key. So triple des is pretty safe. Right? So encrypt, decrypt, and then encrypt again. And then on the other end, you decrypt, encrypt, and then decrypt. There are some books, by the way, they say encrypt, encrypt, encrypt. That's wrong. It's really encrypt, decrypt, then encrypt again. Okay, for the AES, by the way, the AES, if you go to Wikipedia and you type AES and you go to the bottom, a few years ago, I watched a video on how they transpose the method that they scramble the data before they convert it into ones and zeros is very complicated. Wow, it's amazing on how it's being used. They shuffle the data around, and then before they come out with the ones and zeros, and then you can use these 256-bit keys to encrypt the data. So it's probably, I don't know if the video is still in there, but probably it's maybe on YouTube that you can find a video on how AES works. That'll be a good thing to watch. So it's been around since 2001. That's when it's been ratified, and it's and you can see down here, even though it's a very strong algorithm, it uses very low resources. So that means it's very quick. So that's why more and more technologies will use AES as their method of encryption. Okay, so, all right, so AES is what we need to go with. Now, the alternate there is the seal that is out there. This is the Cisco routers don't like to use the seal, so it's hardly ever used. Especially in our network and when it comes to setting up communications between routers and especially when you're setting up VPNs, it's not used as much. But it's out there, and it's an open system. More we use the AES and the SHAs and the MD5s. Okay. Here is the reversed, the RC algorithms, like I told you earlier. RC2, 4, 5, and 6. RC4 is stream. Stream means you take 1 bit at a time to encrypt, a byte at a time. Block is you take a block of data and you encrypt blocks of data, which is a little bit quicker. RC4 is what's WEP is, WEP is based on. WEP encryption for the wireless. And that's then they came up with the TKIP, the temporal key integrity, to make sure that the keys are random. Really a patch for RC4, because RC4 by itself, the WEP was crackable. Again, I'll show you how easy to crack without even guessing what the key is. Okay. Diffie-Hellman key, like I told you earlier, I'll show this is an asymmetric keying, but it's mainly used to transport symmetric keys for VPN, for setting up VPN tunneling and encryption. So Diffie-Hellman is the method. It's an asymmetric algorithm, and it's used to transport symmetric keys across the public internet. And I'll show you how that's done in class. This is the method, but it might be a little bit confusing, but it's based on you come up with 2 keys and you do some dividing and you transport the remainder, and And by doing that, the two guys on the other ends will have the same keys after they use mathematical equations. But I can show you that very easily in class on how it's done if you don't really, I don't want to go over this right now because you have to show it on paper and it's much easier that way. Okay. The PKI, the public key cryptography, explains the difference between the symmetric and asymmetric key, but it's really more of how the infrastructure, how the whole thing works. How do we generate the keys, keep track of them, put out digital signatures, digital certificates and what they mean. The four protocols that use asymmetric key algorithms is the Internet Key Exchange, the SSL. When you do the iKey exchange is when you set up for VPNs. The SSL, the secure socket layer, is whenever you do SSH to allow you to connect to servers. So every time you go in a website that uses HTTPS, you're really using the SSL layer. You're using asymmetric key encryptions to communicate with that website. SSH, when we use SSH in lab to connect to the router for remote access, we use the RSA. Remember, we do crypto key generate RSA. We're really creating a public and a private key. And Pretty Good Privacy also uses it to encrypt and decrypt emails. All right, so those are the four different protocols that use asymmetric key algorithm. Please write those down. Okay. So like we discussed earlier, the public and the private key is what gives you confidentiality. The private key, those two are generated. You keep one, and the other one is the one that you send out to everyone else to use. If anybody wants to send you data, they'll use the public key to encrypt the data. And when you get it, the only key that's going to be able to decrypt it is the private key, the one that you have. And you can go the other way. You can encrypt the data with the private key and you send it out, and everybody that has the public key will be able to decrypt it. And everybody in the public will know, because they were able to decrypt the data, that the sender has to be this guy, whoever this guy is. That's authentication, right? And non-repudiation, I can't even say, hey, I didn't send you this message. How can you say you did not send me this message and I was able to decipher it? The only way I could decipher it is because you send it, right? So that's non-repudiation. All right, so that's what for authenticity, right? Then asymmetric, we talked about that, how we do that with the hashing, the encrypted keys, the Diffie-Hellmans, right? The digitals. Okay, what is the digital? We talked about what digital signatures are, right? That's when you encrypt the data, encrypt the hash that comes out, and you stamp it on the method. All right, so that's what digital signatures are. So let me repeat again what the digital signature are. What you do is, before we get to code signing, digital signature is when you take your message, you run it through a hash, and you encrypt it with a key. The encrypted hash that is stamped on the message is your digital signature, right? So when you receive it on the other end, what you do is you decrypt the hash, the encrypted hash, with the same key, because you were able to decrypt it. Because, by the way, I encrypted it with my private key. I encrypted the hash with my private key, right? Because when I send it to you, you have the public key. You decrypted it with the public key. Now, because you were able to decrypt it, you know it came from me, right? You know it has to be the private guy is the who sent it. That's authenticity, right? That's like, you know, it's uniquely to me. That's why it's like a signature. There's no way anybody else could have sent it except me. Why? Because you were able to decrypt it with your public key. And then once that's done, then you run the message through the hash and compare the number that comes out with the decrypted hash. Now, if the number is the same, then the data is okay, right? The data is okay, and you know where it came from. So that's beautiful, right? All right, code signing. You can actually also use encryption for software purposes, or when you are installing software, to know that the software is authentic and it came from the source, from the publisher. It wasn't somebody else made it up. So they use code signing. When you download and install software, you'll use the codes that you type in. They use encryption methods to make sure that no one else will be able to to make up these codes or figure out what the codes are, right? So they'll use a method to decrypt these codes before you install the machine. So when you type in the code, they'll use a hash method to encrypt to figure out what the actual hash is, compare it with the one that's saved, and if it's the same number, then you know that you're okay to install the data. Or you can compare and make sure that the data that's being installed did not come in from someone else, right? So there are encrypted codes that are placed on the CDs or DVDs that you buy. That's what code signing is. Digital certificates. Digital certificates are used, for example, this is what digital certificates are. I can go to a certificate authority and ask for a digital certificate. What they do is that the certificate authority are the ones that make up the private and public keys. So they'll send it, let's say my name is Bob. They'll send me the public key. They'll generate a private key for me, and then they send me the public key. So I have the certificate and it has the public key in it. That's what digital certificate is. It came from a certificate authority. Another guy named Mike will do the same thing. But let's say he'll have his own certificate. So when Mike wants to talk to Bob, first of all, I go to the certificate authority, says, hey, this guy Mike wants to talk to me. Can I double check his certificate and make sure it's okay? Then the certificate authority will say, okay. And Mike, of course, will do the same thing. So now Mike and Bob can talk to each other because they have the certificates and they've been authenticated by the certificate authority, right? So we use digital certificates. We can communicate with each other using the keys. So when I want to talk to Mike, I'll encrypt the data, send it to the certificate authority. The certificate authority will decrypt the data for me and encrypt it and then send it back to Mike and so on. So digital certificates are used extensively because you don't want to keep. It makes it much easier. So now when you want to go to any website, the first thing that they do is they send you a digital certificate. You download it and install it on your computer. And every time you want to communicate with anybody, you'll use the public key in there to encrypt and decrypt the data. Okay. So what you do, you send in the data to the certificate authority and you make sure that this is the digital certificates. Oh, we talked about the digital certificates, right? How you encrypt and decrypt the data, the hashing. Okay, there are different types of digital signatures out there. Here's, for example, the Ron Rivers, the RSA. Ron Rivers is the RC certificate. This guy, Ron Rivers, is the one that came up with RC2, 4, 5, and 6. Right? He has an extensive amount of contribution to the encryption world. Anyway, so the RSA is only really used. I don't use it for anything else but the SSH. It's again because of how slow it is. Okay. Here's the certificate authority, just like you getting a license. So, for example, first of all, you have to apply and ask the certificate authority for a certificate, and then they'll send it to you. And then you can use your certificate to communicate with anybody else, right? And your certificate will have all the information that it's needed, especially the public key to communicate with anyone, with another, let's say another bank, TD Bank. TD Bank in here, the certificate authority will have their what do you call, their private key, and you use that public key to communicate with them. So every website that you need to go to, the certificate authority will give you a digital certificate to communicate with, and then you'll use that digital certificate to access their servers, right? So it says, first of all, you go to the certificate authority, and they'll give you a certificate, and you store it in here. And then when you want to communicate, first of all, by the way, they issue the certificate authority, and then if you can exchange PKI exchanges with certificates between each other. When you want to communicate with this person right here, Alice will go and verify the PKI certificate that's been the Bob sender, and if it's verified, then these two people can talk to each other, right? There are different authorities. They use different classes depending on what type of certificates they use. They'll send you out. So class 0 is used for testing purposes. If you use a class 1, it's verification of emails, for example, right? We'll have to get into all of that. There are different vendors that are out there. Baltimore, VeriSigns, Microsoft is another certificate authority. Usually your computer knows the different types of authorized certificate authorities that are out there. For example, if you go in to a network that has a wireless connection, and you try to connect to them, they'll try to give you a certificate. And usually your computer doesn't recognize that this is a legitimate certificate authority. They'll say, do you want this digital certificate or not? It's not known. And of course, if you know who you're connected to, you say yes. Because when you communicate with a wireless router, you also use those certificates, those digital certificates. All right, and here's the standards, the different standards that are out there. The PKCS1, the public key cryptography standards, 1 to 15. We don't have to worry about that. Number 7 and number 10 are the most widely used to exchange for certificates between you and the certificate authority. The topologies, you can have single-rooted PKI topology where you have the certificate authorities, a whole bunch of different certificate authorities, or you can have the hierarchical. You have the big guys, the root, and they have subordinates. All right, so please write those down. I know I don't want you to write too much today because I know this is a very long lecture. And I want you to listen more than anything else and really understand the different type, the cryptography and how it works. Hopefully you've been hanging in there. And if you went through this whole thing once, next time you listen to it again, do it in chunks, maybe every 15 minutes or so. You take a break. You don't have to listen to this whole thing. I know it's been over an hour, but that's what it is. Anyway, so write this down, the two different topologies. The single rooted where you have separate authorities that give out certificates, or you can have the root, but he has a distribution authorities, the subordinates, CAs. So you can go to the subordinate CA to grab certificates. Register authority, the RAs are the one that are going to register you, subordinate. So you can ask them, they can register it, and then the certificate authority will send you the certificate. Just like licenses, to make sure that you're authorized. Of course, the certificate authority, a company can go in there to the certificate authority and says, okay, we want to issue digital certificates to anybody that wants to talk to us. They'll generate the private and public keys, They'll keep the private key, and the public key that they generate, they stamp on the digital certificate and they give you that. So you use that to communicate with their servers. That's really what it means. All right. Moving on, digital certificates and CAs. So we just talked about that. Peer-to-peer authentications. Both of these, Alice and Bob will use the PKI to communicate using their certificates. Okay. And that's it. It's been a little, maybe over an hour. But next time, we're going to talk about how we can use all the different types of protocols to set up a VPN. That's what it really comes down to. So when we talk about these different types of encryption methods in VPNs, you'll have a pretty good idea. 87 slides. Wow. All right. Anyway, until next time, I'll talk to you later. Keep up the good work.